So I'm going to have this bond between these two. I'm going to have this bond between, oh my gosh, these two, okay? And then I'm going to have this bond between these two. So if I look in this disastrous mess, I can see that I circled 6 electrons in total, and that's a triple bond. Oxygen is O, and it's got 1, 2, 3, 4, 5, and 6 to make its bond, and oxygen over here, and 1, 2, keeping those valence electrons that are bonded away so that they don't get in the mess of the drawing. And then, so it's going to share 4 electrons in a double bond. 1 right there, and right there. Alright, single, double, triple bond. 2 electrons, 4 electrons, 6 electrons. So that's where it is. All of these are your valence electrons coming from a Lewis dot structure. Erase. Alright, Alright, let's not worry about this too much. We will be making some bonds with a molecular modeling set, which is fun, whatever. But as far as we're looking at these shapes and stuff, let's not worry too much. Electronegativity, I'm going to actually go back to my periodic table. The electronegativity is low right here, and it increases as you go. Fluorine is the most electronegative element on the periodic table because its electrons are closest to its nucleus because it only has 2 shells. And so that's a force that's pulling, and because it's so close to being a full outer shell. Everyone wants to be full, no one wants to be unhappy. So this one down here, lithium, remember from the picture that it had the inner shell with 2 electrons and then 1 on its outside. It would have to gain 7 electrons in order to be happy. So it's not going to do that. That's just too much energy. It's just going to drop the outside one, its valence electron, and be happy that way. So not electronegative, very electronegative. How badly do you want that electron? That's what it is. All right, polar covalent bond. So in a covalent bond, if they don't share politely, then it's going to be polar, as you see up here. Oxygen, look at how huge it is with its big nucleus. It's going to have an unbond or a bonded pair up here, and then it's going to have these hydrogens that are hanging on for dear life down here. These become partially positive. Oxygen becomes partially negative just because the electrons are being sucked. Hydrogen's electrons are being sucked into oxygen's big positive nucleus. So it's all about these forces of attraction. Ionic bonds form when atoms that are neutral either gain or lose electrons. So that atomic number, that proton number, that always stays the same, but the electrons can come and go. So if I look back at the periodic table again, I know that groups 1, 2, and technically 13 are going to be losing electrons because, like I said about lithium, it's going to take 7 electrons to make it happy. Beryllium, it's going to take 6 electrons to make happy. And boron, it's going to take 5 electrons to be happy. Why would they do that when they could just get rid of what they have? So these guys are going to lose electrons, become cations, and become positively charged. Carbon usually participates in covalent bonds, so he doesn't really gain or lose, but I guess he could technically do either. And then nitrogen, oxygen, and fluorine are going to pick up. Now, because we know nitrogen has 5 valence electrons, it's going to pick up 3. And because oxygen has 8 or 6 valence electrons, it's going to pick up 2. And because fluorine has 7 valence electrons, it's going to pick up 1. And you'll always have a periodic table if you need it. Let's see. So ionic bond, and then I listed on Canvas polyatomic ions for you guys. It wouldn't hurt for you to look at those. Alright, so ionic means to transfer, and so here, because it's got that 1 and it doesn't want it, it's transferring it over to chlorine, and now it's because of this positive and negative attraction that it's attracting each other. This used to only have 7 valency electrons on the outside. Now it's got 9, but its proton number didn't change. So now you've got the proton's inside of here, but you've gained an extra electron, which means you're going to be a little negative. Here we had 1 on the outside, which meant it had 11 protons and 11 electrons, but over here it's got 11 protons and only 10 electrons. So it's become kind of positive. Well, it has become positive. And because of this attraction between positive and negative things, that's how the ionic bond forms. Most ionic bonds are going to be salts, calcium chloride, potassium chloride, stuff like that. And they create crystals, and it's a ratio. So how many do you need? So sodium and chlorine is a 1-to-1 ratio. You only need 1 to fulfill this. All right, let me do some drawing again. I know it's horrendous, but we're doing it. All right, so I've got magnesium, and if I look at my periodic table, I want to know how many, oh, won't it let me go? No. It wants to know how many valence electrons I have. So I'm pointing to it. It's in group 2. So I know that it's got 2 valence electrons that it's going to want to get rid of. So that means once it does, it's going to be a positive 2. Okay? And if I draw magnesium as a Lewis dot structure, I'm going to take magnesium and I'm going to give it 1 electron here and 1 electron here. And I want to bind with chlorine. And so chlorine, we know, has 7 valence electrons. So I'm putting them all around. And now what I have is this. So I know that this electron is going to transfer over here like this. All right. And now that makes 2 on this side and makes this for a total of 8. I don't have any place else to go with this. So I'm going to need another chlorine. And I know it's got, oh, I don't know what's going on. Stop. What? Why? Okay, anyway, it's got 7 valence electrons as well. These should be dots, but you know, whatever. So now this electron is going to transfer to here. So when you come up with a chemical formula for this, the cation is always listed first. So it's MgCl2. And that would be your formula because you've got 1 magnesium and 2 chlorines. So the anion for chlorine, its charge would be -1. So when it picks up 1, it's going to become -1. When this loses its 2, it's going to become +2. So if you remember from 10th grade chemistry, you can say, all right, well, this has a +2. How many chlorines is it going to take to fulfill the +2? 2. All right, what do I write here? Considered a weak, okay. Yep. Weak chemical interactions, we've got hydrogen bonds, and we get to draw those. And we've got van der Waals forces that are not always around. Van der Waals forces come and go, and you can read that. These are going to be important in Chapter 3 for water. Again, with these orbitals, don't worry about this. Here is your hydrogen bond. There's a question on a quiz that makes you say, where is this hydrogen bond? It's always going to be represented by these dotted lines, and we see the partial positive charge of a hydrogen is attracted to the partial negative charge of nitrogen. All right. Making and breaking, we've got reactants on this side, they're doing the reacting, and then we get products on the end. And you need a line to say that it's going someplace or doing something. So we'll look at balancing those, and then, yes, I put there's a whole chapter on this, on photosynthesis and cellular respiration, and labs on it too. Ooh, dynamic equilibrium. When you're reading that, dynamic, if you remember from physics, means that it's moving. So when the questions on the test try to confuse you by saying that the reaction isn't happening anymore, make sure that you remember that it's a dynamic equilibrium, so that means it's got to be moving. If it's, this was from physics, if it's static equilibrium, then it's not doing anything. Right, chapter review. Oh, and then I don't need to say anything about this, but at least you have it now, and that's fantastic. So that's it. 30 minutes of me talking, it's like a lecture in class, and I would never do this to you. Turn me off, turn me on whenever you want to. Fast forward me, it doesn't matter. But that was just trying to give you an overview, and it will not be like this in class, okay? That was brutal. It will not be like this. All right, thanks, you guys.